Okay, finally. Shall we? Um, Last week we talked about power series. Just want to remind you what the hell we're talking about. Around some A. Huh? Um, I'm not saying they're not connected at all, but we talk about series, yeah, infinite sums, and binomial expression is always a finite sum. Is it big enough? Is you big enough? As Rihanna once asked. Yeah. Um, we mentioned that the domain of convergence of a power series is always an interval, is all of R, or the point itself, which is interval with radius 0, and or a symmetric segment around S. In other words, exists a number R such that the series converges for x's between a minus r and a plus r, and diverges for x's smaller than a minus r and x greater than a plus r. We said that when the domain of convergence is all of the real numbers, we can consider it as a case where which the radius r is infinity. And when the domain of converges only the point A, we can think of it as the case where r, the radius, is only 0. R is called the radius of convergence. We talked about it last week. This is the pointwise convergence of power series per series. And what I want to discuss today is the uniform convergence of power series. What is this? Uniform. One last thing. We There are two ways, equivalent ways to calculate R. R is one above the limit of n plus 1 an, or the limit of the nth root of the absolute value of an. We talked about it that R doesn't necessarily exist. And when we talked about it in Infi 1, which is very fun, we talked about the lim sup, not just the limit, but here in Infi 2, all of this is not very important. It's my choice. You have a lot of syllabus to achieve. Can't take our time with every little subject. Okay, so what I want to talk about today is the uniform convergence of power series. Um, Let me remind you why uniform convergence is important. In order to integrate what we call part by part or element by element by element, we need the series to be uniformly convergent. Uh, for this one, when we want to integrate all the series, and let's write it precisely. Here's something we can actually integrate every element by itself, which basically gives us the following series an with x minus a to the power n plus 1 above n plus 1. For example, if we look at the geometric series, we perform integration element by element, we get that the integral, let's say from 0 to some t of 1 above 1 minus x minus t. So it should be t, right? Um, Minus t dt is the actual sum of the integrals of every element. So here it's 6 to the power of n. Which gives us the sum of 2 to the power of n plus 1 above n plus 1. That's what we called 2 weeks ago, integration element by element. And similarly, in order to derive, or whatever you say, differentiate, um, differentiate element by element, we need the series of derivatives to be uniformly convergent, and the series itself, what is it? In the middle of December, the winter. Itself to be convergent at some point of the interval. Or at some point, that's all. That's a theorem we mentioned 2 weeks ago. So it is important for us to know, yeah.
Sorry. Integrate element by element, you integrate
2 weeks. That's your problem.
by t and then integrate by x.
No, I integrate by t and then I substitute x instead of t. That's a definite integral.
Okay.
So, We've already mentioned it. We show an example. Let's show another example. Let's say, for example, let's say we want to calculate the following sum, or the sum of the following series. N goes from 0 to infinity, n squared above to the power of n. Can why is it important? From my point of view, we can talk about other point of view. Points of view. We'll talk about it later. Probably in lecture number 18 or something. Let's say I want to calculate the sum of the following series. Now, how do I reach these kids? How do I get to this sum? We start off at the geometric sum. We actually don't have another starter. As I mentioned earlier, not today. Beginning the next lecture, we're gonna have two additional starters. One is the sum of e to the power of x, and one is the sum of sinus x. We're gonna have three starters, like Pokemon. But right now, we only have the geometric series. The question is, what actions should we do? Should we apply on the geometric series in order to achieve this sum, this series? So we start with the geometric series, and this is the geometric series. It equals 1 above 1 minus x. What can I do to achieve this sum? So at one point, we should put x is equals half to get this to the power of n in the denominator. But before that, we need to get the n squared in the numerator. So the question is, what kind of, I don't know, action? Log of 2? No. It's probably easier from something I talked about earlier. If you derive element by element, differentiate element by element, the geometric series, you get on one hand the sum of n x to the power of n minus 1, and on the other hand, the derivative of 1 above 1 minus x. Let's write down that way. Do it in a underset. No, that's completely overset. And we say that we differentiate element by element to I. Need just one. Do it nicely. Differentiate. What's the derivative of 1 above 1 minus x? I'm doing it in my head, so maybe I'm wrong, but it's 1 above 1 minus x squared. And okay, in order to get n squared in the numerator, we should probably differentiate again. But if we differentiate here at this point, what we get is n minus 1 jumping out. That's what we say in Hebrew, and not n. How do we get n to jump out? With the n outside, it becomes n squared. We can, and we will, multiply each part of the equation by x. Now, considering this, the variables, the series is n, this is the one that's running, that's the index. Multiplying by x is just multiplying by constant, which doesn't change the convergence at all. So we have x here, and right now we can differentiate again. Differentiate again, element by element. And here the n goes out, meets his own n friend. They become together n square. And we should find the derivative of this function, which is write down explicitly. Derivative of the numerator multiplied by the denominator minus the numerator multiplied by the derivative of the denominator with the minus 1 as the inner derivative. Denominator squared. What is this? Why is it like this? First of all, we can delete 1 minus x from each element. Secondly, it is minus minus, which is plus. And we have 1 plus x, 1 minus x power 3. And finally, we can again multiply each side of the equation by x to achieve, on one hand, x to the power of n here. So multiply x to the power of minus 1 with x, we get x to the power of n. And on the other hand, multiplied by x, we get, well, x multiplied by 1 plus x. Finally, we can put x equals half, and we can get our sum. Yeah, considering our poor ability in calculating sums from into 1, here, a whole new world. Yeah. Of calculating infinite sums. Of course, we're not able to calculate every sum, but every sum that is similar to a power series, with enough trying, we could probably do so. What is this number? Hopefully, I'm not wrong. And all this that. This is a half. It is quarter. It is 6, as far as I can see.
Okay, each of the steps you have to prove that the derivative is uniformly convergent.
Yes, so we have to. We have two things here that need to be proved. And multiplying by x, that's multiplying by a constant. It's totally fine, whatever the series is. But differentiate element by element requires us to know that the series of derivatives is uniformly convergent. I mean, here in this differentiating derivative, we need to know that this series is uniformly convergent. And here we need to know that this series is uniformly convergent. Putting, yeah.
Every time you differentiate, you have to prove that the differentiation.
So I want to answer this question right now, generally. Talking about every power series, what can we say about its uniform convergence? About its uniform convergence itself for the integration element by element, and about the uniform convergent of the series of the derivative. Now,
It's like inductive. Well, if it is uniformly convergent, obviously the volume concept has to be.
in some kind of a yes. We'll see right away that the radius stays the same. It's the same r. So basically, uniform convergence in every segment, but I'll write it down explicitly and formally. But I want to say that's the main question here. Why can we differentiate and talk? Generally speaking, why can we talk about differentiating element by element and integrating element by element when it comes to power series? But there is another little point here. We can put x equals half only if we know that the series is pointwise convergent in x equals half. We can actually plug it in. Basically, it's kind of the same answer. We see it right away. The original sum is convergent in at x equals half, so the New sum will be as well. But let's say that way. That's very nice. Let's say that. Very nice. But we need to know that the sum or the series of derivatives are uniformly convergent in order to do so. Yeah, this 6. Now, we can check it out using our Weierstrass theorem, blah, blah, blah. But as I already give you a little spoiler last week, we actually do not need that when it comes to power series. Okay. Now, on one hand, we know by Weierstrass, thank you, big W. I have to write it down something like that. Weierstrass. Weierstrass that if the series is absolutely convergent, it is uniformly convergent without writing down explicitly the theorem itself. Now, in lecture number 16, on the other hand, lecture 16 was fun. We showed that if the series, write down the series, sum of an, it's going to say to the power of n, is convergent at some b, then it is absolutely convergent at every c that satisfies the distance between C and A is smaller than the distance between B and A. So why do we get by these two? One hand on the other hand. So we can conclude that the series an x to the power of n is absolutely convergent. Thus, uniformly convergent. Too many ends here. Uniformly convergent.
Fun. You remind us that we have fun.
Yes, it's not just fun, it's fun factorial. Yeah. That's uniformly convergent. In every closed segment contained in the domain of convergence. I'm going to say, for example, we know that the domain of convergence of the geometric series parallels n is -1 by 1. Yeah. It's around 0. Do you want to say that? No. Take some c, which is smaller than 1. Then by the proof of our of the theorem from last lecture, which is fun, etc., etc., we get that it is absolutely convergent there, and so it will be uniformly convergent in these segments. So for every c smaller than 1, we can say that the series is uniformly convergent in a segment between minus c and c. And generally speaking, we can say it is, as we already mentioned, uniformly convergent in every closed segment in the domain of convergence. At least, yes, we have to put one little star here. A segment that does not contain the edges of the segment without the domains ends. I mean, if it's not the case, but say that the domain of convergence of the geometric series was -1 to 1, including -1 and 1, we know that it is only pointwise convergence at 1. At every point smaller, actually not smaller equal, smaller than 1, we're gonna have uniform conversion. But right now, by our theorems and proofs, we can conclude that in every closed segment without the ends, the series is uniformly convergent. Yeah.
If
It's rainy.
when you're using B and C, is B like we would substitute B into X and C into X?
Yes.
Good.
So we know that in B, the series of an b minus a to the power of n is convergent. We can say that but every c that satisfies c minus a smaller than b minus a, the series is uniformly convergent at x equals c.
Thinking the probably when branch of case, how do we solve for the n? That's how it.
It's one of my questions, but not the question I want to answer right now. Because what do I answer right now is, as Sammy mentioned by induction or something like that, how do we talk about the series of derivatives and its series of derivative, what we used here in our example? On the other hand, how can we talk about the series of integrals? So right now, the series itself is uniformly convergent. That's very nice. We integrate element by element one time, and then boom, it's another series. How can we do it on and on without stopping and proving it is uniformly convergent in every step? Yeah. So, but what about, say that, say age here? That's very nice. But what can we say about the say radius of convergence of the series of derivatives slash integrals or anti-derivatives. So here, a nice little proposition. I'm going to explain it later. Let sunshine in, let this one be a power series. And let R be its radius of convergence. Now I claim that the series of derivatives that we get from differentiate element by element is n jumps out an x minus a to power n minus 1. And the series of antiderivatives of integrals of integrating element by element. I'm not working for him. He's working for me. Sure. Yes. Series of antiderivatives is an some an, and we divide by n plus 1 x minus a to the power of n plus 1. We integrate element by element, we derivate element by element. That's what we get. Now, I claim that the radius of the series of derivatives and the radius of the series of antiderivatives are the same as R. The derivating element by differentiate element by element, integrate element by element, you get the same radius, no matter how many times you do it. Denote the radius of the series of derivatives with, let's say, small r, r1, and the radius of the series of antiderivatives r2. Then R1 and R2 are both actually R. In other words, differentiate slash integrate element by element. How many times you like? The radius still stays the same. Now, what does that mean?
And wait, it's around the same age, right? Because we keep the same age.
Yes. What does it actually mean by whatever we told? Till this very point, we can, when it comes to power series, we can differentiate slash integrate as much as we need. Inside the domain of convergence. What do I mean by inside? Not including the ends. Okay, without the domain of ends. It will be perfectly legal, mathematically correct. That's because the series is uniform convergent in every closed segment. Let's say if the geometric series has its own radius 1, which means that the convergent domain of convergence is between -1 and 1, maybe with the ends, maybe without them, but it's between -1 and 1. So in every closed segment inside, for example, minus half to half, the series is going to be uniformly convergent. Now, because differentiate or differentiating or integrating element by element it does not that does don't change the radius, the segment, for example, minus half to half, is going to stay inside the domain of convergence, which means the new series, be it the integration or differentiation, is still uniformly convergent in this segment. And we can do it on and on and on, how many times we need. So we don't need to stop and prove that the new series is uniformly convergent. By what we say, generally speaking, for every power series, it is true, which is convenient. Don't have to use Weierstrass or any other method. We can just say, you know what, it's inside the domain of convergence, and how to find R and the domain of convergence we've already showed in lecture number 16. As long as it's inside the domain of convergence, we can say, you know what, you can differentiate and integrate how many times you want. Yeah.
Just for the people who may rewatch the Zoom, could you explain, just go over Weierstrass?
Yeah.
Did I often hear that during the
It was lecture 14 or 15. Probably Nero talked about it today. Another color. Any references?
we like teal.
Teal.
Olive.
Olive. Okay, okay.
We said it's bad, but okay. Oh, olive's bad.
No, olive's not bad.
I thought we said lime was bad. Lime was bad.
Lime is also extra. Lime is no. But olive is good. I like brains. Weierstrass. Let it's general theorem. It's for every function series, not just power series. Let there be a series of function. There is number series of numbers. And such that it's convergent. Convergent series an such that an is greater or equals f and x. Who is that? Who are you? I don't know. F and x for every x and I, and for every n in n, natural number, index. Then the series of functions is uniformly convergent. So what is basically written here that if the series is absolutely convergent because it has absolute value and is smaller than a convergent series, then it is uniformly convergent. And what we talked about, as far as I can remember, it was lecture number 15, maybe it was 14, I think it was 15. We show that if the series is uniformly convergent, it isn't necessarily absolutely convergent. Talk about what we can do in such cases. But in my words, what Varshas basically says is that if a series is absolutely convergent, then it is uniformly convergent. So then back to our corollary. So no, this nothing to add. It's phrased good enough. When it comes to power series, we can definitely integrate as much as we need inside the domain of time. So let's add it. So in our example of n squared above to the power of n, everything is legal. Is authorized.
Well,
No, we don't have to.
would there be questions where we'd have to differentiate it or integrate and then have to prove that the differentiation or integration?
I'm not saying that they're not going to be, because if it is a series of functions that is not a power series, let's say it's sinus n x or something like that, then we need Weierstrass or any other method to prove that it's uniformly convergent. My theorems here in the corollary speaks only about power series. On the other hand, we don't usually ask questions about that, so one can expect questions like that. Calculating sums of infinite series using differentiating and integrating is common kind of questions in the final exams, but we don't, and these questions are basically almost 100% technical. You don't have to explain anything mathematically because our corollary about power series do it automatically. My preferred structure of test is 5 questions. Each one of them is 21 points, so you can add up to slightly more than 100.
You like pop
No, it's five questions. No, some of the questions have 2 parts, 10 or 11 points, it depends. And I try to take sample from every part of my course. I mean, indefinite integrals, definite integrals, improper integrals, sequence of functions, series of functions, and that's it. Without nachs, we say in Hebrew, but it's going to be easier than Infi one. It's not going to be easy. It's going to be easier than Infi one. The main reason is that.
And your Infi one, not our Infi one.
What?
Than your Infi one, ours is.
And yours Infi one as well. Hopefully. 2 reasons. First of all, you are grown-ups now. The first chalk of academy is long behind you. And secondly, that the last part of our course about the multivariable calculus is absolutely technical. No proofs at all, only differentiate and equal 0 and solve the equation, which is easier. 20 or 30 points, something like that from the test is going to be on that material. Multivariable calculus. F, X, Y, Z is whatever. Yeah. Okay, so you asked the question, which we still didn't answer. What about the ends of the domain? I mean, let's explain a proposition, okay, and then get to the corollary. Corollary. Explanation of the proposition. Explanation of proposition. That's what George Washington said to no, that's the Emancipation Proclamation. The Emancipation Proclamation. Explanation of the proposition. We know that the radius of convergence is, for example, the let's say the limit of a n plus 1 above a n, all that in the denominator. Now, this is why it is only an explanation and not proof, because we know that it is not actually true. Sometimes the limit doesn't exist, sometimes it's hard to calculate, but considering our main interest here in power series, it is fine to write it down that way. And now, and so, if we consider about what I call R1, which is the radius of this series, here in this series, the coefficients are not an, they are n multiplied by an. So if I run down a simple formula, I have to multiply an minus 1 by n plus 1 and an by, and let's write down explicitly in English. The coefficients of the series of derivatives are nan. So we have, but right now, what is the limit of n plus 1 above n? We know that this is 1, right? So we can multiply by n plus 1 to n, which goes to 1 when n goes to infinity. Let's write it down with the little bracket. Oh, right, left, left, right. Confusing. When I write in Hebrew, when I push the right arrow, it goes to the left, and I'm used to it. Sometimes I miss, which is the same R, same as R. I mean, more intuitively speaking, what determines the radius is the ratio test or the nth root test. And we know since in Phi1, which is very fun, that poorly things like polynomials and n plus 1, they do not change anything when it comes to the ratio test. They all goes to 1. The same goes for the nth root test. If somehow derivating was, plugging out some to the power of n, well, it changes everything. But it's not the case. And it goes the same for the integration. The coefficients of the series of antiderivatives are an. After we integrate, we get an above n plus 1. So if we want to calculate what we called R2D2, an plus 1 above n plus 2, and an above n plus 1. But yet again, the n plus 2, n plus 1, what can they say when it comes to ratio test? Nothing. Yeah, that's 1, that's 2. Is going to 1, and we have the same R. So yet again, the technical message here is that we can integrate and we can differentiate element by element as many times as we want. But we still have your question. What about the endpoints? I mean, let's guess it. Yeah. What about the endpoints? I mean, for example, we've already done it earlier. We know that series of geometric series is uniformly convergent at every -1 to 1, and let's write it down that we integrate here. Okay. So when we calculate, we get on one hand, the antiderivative of 1 above 1 minus t is minus ln 1 minus t. And let's write down more visible absolute value. Let's write down more visible brackets. We can put t is 0 and t is x. On the other hand, when it comes to the sum, the integral of t to the power of n is t to the power of n plus 1 above n plus 1. And yet again, when we put t is 0 and x, and we are left with 0 gives us ln 1, which is 0, and x gives us minus ln 1 minus x. And on the other hand, we get the series of x to the power of n plus 1 above n plus 1. When we put t is 0, everything is 0, so I don't write it down. So right now, for can the original series original series is divergent at x is -1. Put here -1, divergent series. However, the series of antiderivatives is convergent. What is the G? Convergent at x -1. I mean, if you put x -1 here, yeah, you do get a convergent series by Leibniz or Dirichlet, whatever you call it, -1 an alternating series. But can we say that putting here -1 is a legal move or it is illegal? So on one hand, the series that we have right now is convergent at -1. On the other hand, integrating element by element, which yields this equation, is only, or as far as we know, is true only when we have uniform convergence. And at 1, at x equals -1, excuse me, etc. At x equals -1, the original series was not uniformly convergent, was not even pointwise convergent. And this problem, this question only emerges at the endpoints, because for every point inside the interval, inside domain of convergence, we already know that the series is uniformly convergent and we can perform integration element by element. So first of all, is it legal? Can we say that? And secondly, we can ask about, you know what? We said exactly what happens to the radius of convergence when we differentiate element by element or when we integrate element by element. Nothing. It stays the same. What can you say about the convergence at the endpoints? Can we say something, oh, you know what, when you integrate, what happened here? The original series is divergent, integration element by element, boom, the new series is convergent at the endpoint -1. Is it always true? Is there any case where it stays divergent right here at x equals 1, it stays divergent. Even after the integration, you put x equals 1 here, you get the divergent series. But is there any example where integration element by element gives us a new series that is divergent at some endpoint, while the original series was convergent at the endpoint? Yeah, and this endpoint. So these are two questions, and I want to answer them both.
Is the integration of a function always bigger than the original?
It's the other way around. I mean, yes, if you look at that's the intuition behind it. If you look at the series of integrations, and we're considering only the coefficients, right? It is actually smaller than the original because you divide it by n+1.
It's smaller, okay. But the range of convergence, it's because the range of convergence is between -1 and 1.
Or, generally speaking, it's the same radius. You look at the same segment.
Yeah, but n+1 is always bigger because it goes to infinity.
Yes.
Yeah.
And the other way around, when it comes to derivatives, intuitively, the coefficient when you differentiate is bigger. So this is my second question. Yeah, for my first question, is it legal? Yes. And generally speaking, you know what? Let's answer the second question first, and then move to this question. Generally speaking, we can ask. Oh, generally, we can ask how integration slash differentiation element by element affects, it's with A or with E? The verb. The verb is with A. It's something weird is word, right? It's with E, with A, whatever. Affect the convergence at the endpoints. Without proof, but kind of an explanation. As we can see in our example, the geometric series, the original series can be divergent at an endpoint, while the series of antiderivatives after integration element by element is convergent there. And moreover, we can see that integration, that the original series is divergent. Specifically, that the original series is divergent at an endpoint, and the series of antiderivatives is divergent at this endpoint as well. I mean, here for x equals -1, the original series is divergent, while the new series after integration by element is convergent, and Ax equals 1, they are both divergent. Now, I claim, without any proof, don't have time, don't have the will, that it is always true. If you integrate element by element, a divergence at an endpoint can become a convergence, but not vice versa. You integrate element by element. The original series is divergent at an endpoint. The new series can be divergent or convergent. But if the original series was convergent at an endpoint, the new series of antiderivatives, after you integrate element by element, must be converged as well. What cannot happen? It is always the case in different words. In other words, if the original series is convergent at an endpoint, then the series of antiderivatives, the series after we performed integration element by element, is convergent at this endpoint. Now, intuitively, intuitively, which is totally enough right now, intuitively, the coefficients of the new series a n above n plus 1 are smaller than the original, which are just an. So if it is convergence with a bigger greater, whatever, coefficients, and it is convergent with the smaller coefficients and above n plus 1.
So, the opposite.
Yeah, well, kind of, yeah. Let's write down for derivatives. It is the opposite. It's not the opposite mathematically speaking, right? If the original, it sounds in English / Hebrew like the opposite. If the original series is divergent at an endpoint, then the series of derivatives is divergent at that endpoint as well. I mean, integration, in other words, integration element by element can fix divergent endpoint into a convergent one, and derivatives, differentiate element by element can destroy a convergent endpoint, make it a divergent one. And yet again, the same intuition. Then the intuition is the same. Now the smaller coefficients are the coefficients of the original series, which are an, while the greater coefficients are the coefficients of the series of derivatives, which are n multiplied by n. After we differentiate, the n jumps out. That's what we get. Now we can let's say it again out loud. What is not written here? If we start with a divergent endpoint and we integrate, it can still be divergent, or it can change to a convergent one, and vice versa. When we start with a convergent endpoint and we look at the derivatives, it can still be in convergent, or it can become a divergent point. But integration element by element preserves convergence at the endpoint, and differentiating element by element preserves divergence at an endpoint. That's the bottom line here. Any questions? So, yeah.
No, so if it's convergent, it can also become divergent?
When you differentiate?
Yeah.
Yeah.
Did you write it?
No, I explicitly wrote down only what is always true.
So it stays divergent for sure.
Yeah. Stays divergent. So when we integrate, it stays convergent for sure.
Does this answer our question of if we can use this or not?
No. Now back to our question. We integrate element by element. And the new series is now convergent at an endpoint. It wasn't convergent before we integrate. Can we say that it is the series and the function are equal at the endpoint as well? This is our specific case. Here it x equals -1. Does this equation hold? So basically, why do we know that integration part by element is legal? Because the series is uniformly convergent. Now, the point -1 is an endpoint, which we cannot right now explicitly say anything about the uniform convergent at a segment that contains an endpoint. All of our all the journey we went through was about -c and c inside the domain of convergence without the endpoints. So what can we say about um, closed segments that contain one of the endpoints? Now, if the series is divergent at an endpoint, it's not even pointwise convergence here. We have nothing to talk about. But when we perform, for example, integration element by element, and we get a series that it is convergent at one of the endpoints, can we say, you know what, there it is uniformly convergent as well, even though it's not originated in our sequence of theorems and corollaries. So the answer is yes. How convenient. Generally, in general, we can conclude that, writing a different sentence, that and some x means the power of n, power c, be a power series. Then the series is uniformly convergent in every closed segment contained in the domain of convergence, even if it is containing or even with endpoints. For example, we can say that this equation holds, and if you multiply everything by -1 or changing the sides, you get a nice little, just for your noting, the series -1 to power of n above n, which is a very basic example, infinity 1 and infinity 2 as well, actually equals ln 2.
We did it.
Hmm?
-1, 2.
No, I changed the here it starts with -1 plus half minus third, but I start with 1 -2 plus third, so multiply everything by -1, which is nicer. Okay. Okay, we can stop here. We will discuss on Tuesday. Oh no, Tuesday we don't have a lecture. Sabbath event. But next Sunday we will discuss, as I already spoiled, the Taylor series. Yeah, how now we talked about how a series equals a function and why is it good. For example, calculating sums of infinite series. How do we calculate the sum of n squared above 2 to the power of n? We use the fact that the geometric series equals this function. And we integrate, differentiate, whatever rate. But the other way around is also very important. Knowing that the function can be written as a C power series is important, and this direction of the equation between power series and a function is going to be discussed in the next 2, even 3 lectures. Gonna be fun, factorial fun, so you should come. Any questions before I close the recording?
Yeah, wait, can you just go back down?
Sure. Sec. Yeah.
I had a question on the last thing.
Yeah.
Um, so we're saying that the power series is uniformly convergent in every. What do you mean by closed segment? Like
Including the endpoints, yeah. Square brackets. And not the circle one.
right. Like as opposed to it not being like I'm confused.
As opposed to what we said earlier.
How we said that.
Earlier, we said that it is true for every closed segment that is not including the endpoints. I mean, if the series here is convergent between 1 and -1, including -1, by our first corollary, we didn't know that it is uniform convergent in, say, -1 to 0, even though -1 is inside the domain of convergence, because -1 was one of the endpoints. And right now we can say it for segments that include the endpoints as well. So basically, when it comes to power series, we can do whatever we want, differentiate, integrate, as long as the series is convergent. Because the uniform convergent comes freely. What?
When it's one, it is, right?
Yeah, it's not.
So any closed segment from anything between -1 to 1.
No,
Like any C between -1 and 1 to 1 is going to be not convergent.
No, it's not going to be uniformly convergent, right?
Right. So then from -1 to 1 is not uniformly convergent. Then.
That's right. But from -1 to any point smaller than 1, -1 to 0.999 is going to be uniformly convergent.
So then why do we? Oh, right. Okay. Never mind. Okay.
Any other questions? Yeah.
In this case, it was pretty clear that it was convergent.
Yeah.
But in cases that it's not so clear, you have to prove it some other way.
Yes, we know how to find R, so it leaves us with the endpoints. And the question about endpoints is about 2 different number series that we know how to use our comparison test or whatever is needed to find out if it's convergent.
Is there any way to give another example, a different example of the thing that we discussed?
Yeah, I mean, we're running out of time, although you ran out of time, but if you integrate this equation one more time, which is not trivial because the integral of ln requires some integration part by part or something, but if you do integrate it another time, the new series is going to be convergent at 1 as well. Because you're going to have n+1 and n+2 in the denominator. When the denominator is n+1, n+2, which is n squared, it is a convergent series. And then you can put a x equals 1 in both sides of the equation, and it still holds. Which right now is not true because the side in light blue is divergent, not convergent. Okay.
Because it's just right because of like pieces. Okay.
Yeah.